Hi everybody, this is our lecture 10, part 2. In this lecture, we're going to see how to perform a chi-square test on a contingency table. That is, we're going to see how to perform a chi-square test for any dependency. Okay, so for example, if you want to see whether the eye color is dependent on hair color, or if there is any relationship between two species living together, yes, or living in the same habitat, yes. So all these, that is comparing any relationship between any two categories or several categories, can be done using a chi-square test. And sometimes these categories or these variables are represented using a contingency table, and a chi-square statistics will help you to compare the variables to test the dependency. So that's what we're going to see. Okay, so we're going to take an example to understand how to perform a chi-square statistics using a contingency table like this. Okay, so let's take a random sample of 223 males categorized by their hair color and eye color. So you have red hair, brown hair, black hair along the row, and blue hair, green hair, blue eye, green eye, brown eye along the column. Okay, so what is contingency table? When qualitative data is arranged in a table like this, so that the frequency in each cell or each cross category is shown, it is called a contingency table. Okay, so that is a contingency table. Okay, a very good example of a contingency table. Okay, now as usual, if you want to test a hypothesis, you have to first start with stating a null hypothesis and an alternative hypothesis. Exactly like how we did in the part 1, we are going to start with stating the null hypothesis and alternative hypothesis. In this case, null hypothesis you state by assuming that there is no dependence in the data. And the alternative hypothesis, as usual, will be opposite to the null hypothesis, which means there is a dependency. Okay, so once you state the null hypothesis and the alternative hypothesis, you have to calculate the expected frequency, because we already have the observed frequency here. Yeah, we already have the observed frequency. This is the observed frequency. That is, there are 52 men who have red hair and blue eyes. There are 26 men who have brown hair and blue eyes. There are 9 men who have black hair and blue eyes. So, and similarly, you can read the rest of the table. Yeah. So we have the observed frequency. Now we have to calculate the expected frequency. But unlike the goodness of fit test, here you have to first determine the row total, column total, grand total for the observed frequency. We're going to see that. And then we have to calculate the expected frequencies. So once you calculate the expected frequency and you already know the observed frequency, you can calculate the chi-square statistics for each cell. Okay, we're going to see that, yeah, with the example. And then you're going to compare it with the critical value of chi-square for a given degrees of freedom. Okay, I'll come over to this when we go through the example. And then we have to decide whether the critical value is significant, or not significant. And based on that, you're going to accept or reject the null hypothesis. Okay, let's start it now. So we have our contingency table here. We're going to test whether the eye color is dependent on the hair color in men or vice versa. To do this, we first assume that all categories are independent of each other, and that is, there is no association in the data. We're going to assume that there is no dependency in the data. So that's our null hypothesis. Once you state it, it's qualitative data, so that is why we are writing it like this. Okay, you have to state the alternative hypothesis, which is opposite of the null hypothesis. Okay. So when you state the null hypothesis, we just assume that the man's hair color is not dependent on his eye color, or other way, vice versa. Okay. Now, alternative hypothesis will be there is a dependency, that is hair color influences eye color. Okay. So that's our alternative hypothesis. Okay. So just like a goodness of fit test, we calculate the frequencies that would be expected under the assumption that the null hypothesis is true. That is, there is no dependency. Okay, so we're going to calculate the expected frequency now. And how do we do that? First, we have to find the row total, column total, and grand total. Okay, let's do that now. Yeah. So what is the row total? First row is, we have 52 men with red hair and blue eyes, 26 men with brown hair and blue eyes, 9 men with black hair and blue eyes. So we're going to find the total of each row by adding them. Okay, so you add them all and then find the row total, add them all, find the row total, yes, to find each row total. Okay, to get the row total. Okay, similarly, you add the column to get the column total. So that's equal to 83. Add 9 plus 24 plus 10 equal to 43. So once you have added all the total, then finally, row total and column total, you add all this total along this column to give the, that is, you're adding all the all the column totals to get the grand total. Similarly, you're adding all the row total to get the grand total. So once you have finished calculating the row total and the column total and the grand total, you can start calculating the expected frequencies. Yeah, what are the expected frequencies? Remember, we are just assuming that the null hypothesis is true. That is, there is no dependency. So consider the red hair and blue eyes. That is, men who with red hair and blue eyes. So we have 52 men here. So so we're going to find for this cell how to calculate the expected frequency. So, and then we'll find for each cell. Okay. So let's just concentrate on one cell, the first cell. Okay. The fraction of men with blue eyes is, how many men have blue eyes? 87 out of 223 men have blue eyes, isn't it? Yeah, 87 out of 223 men have blue eyes. Of these, how many have red hair? 97 times 87 over 223 will have red hair and blue eyes. Yes, agreed? Yeah, so there are 97 men with red hair. The number of these we would expect to have blue eyes is 87 over 223 times 97. Or I can rewrite it as 87 times 97 over 223. Now look at this carefully. What is 87? What is 87 here? 87. 87. What is that? Yeah, what is it? Oh, it's a row total, isn't it? Similarly, what is 97? What is 97? Column total. So you have in the numerator row total times column total over 223. What is 223? It's a grand total. So you have row total times the column total divided by grand total. So we have a formula for expected frequency for each cell now. So we can rewrite this in a formula like expected frequency is equal to row total times column total divided by grand total. So now you can use this formula to calculate expected frequency for each cell, okay? Yeah. Now, what I want you to do is, I'm going to show you one of them, like how I've done that, yeah? So we have calculated for the first cell, yeah, the expected frequency. This is your expected frequency, okay? Now I want you to calculate the expected frequency for men with brown hair and blue eyes. Similarly for each cell, and write it down. Well done. Thank you, guys. Good. That's correct. So notice that the expected frequency must have the same row, column, and grand total as the observed frequency, because you are calculating the expected frequency based on the fact that the null hypothesis is true. And the process of calculating expected frequencies essentially divides each column total in the ratio 87:97:39. And these are the frequencies if we would expect, if hair color does not influence the eye color. Remember, null hypothesis is true. That's what we have assumed. Okay, so now we have done this part, the first step. We have done the second step. We have done the third step. Let's go to the fourth step. Yeah, that is calculating the chi-square statistics. Again, we know the observed frequency. We know because that's the experimental value. Yeah, what we have observed. We have calculated the expected frequency. We know this, so we can surely calculate the chi-square for each cell. Okay, so we will calculate the chi-square for each cell. So comparing the expected and observed frequency, I have just written both together. That is your observed frequency. In the bracket is your expected frequency. It's always good to represent it in a table form. It allows you to read and explain to others easily. Yeah. So that's how I have represented observed outside the bracket and expected frequency inside the bracket. Okay. Now we can calculate chi-square for each cell by subtracting the observed frequency with the expected frequency, squaring it and dividing it by the expected frequency. So you calculate for each cell. And I want you to use your calculator and find the value of chi-square. What did you get? Use your calculator, please, and find the value of chi-square. Very good. So you got 16.68. Yeah, good. So what does this mean? We have a chi-square value now. Then what will be the next step? We have to compare this with the critical value, just like how we did in part 1. And for that, yeah, you have to check, isn't it, whether it is significant enough to make a decision whether to accept or reject the null hypothesis, or whether it is a chance event. Yeah. Okay. So for that, you need to use a chi-square table, and to use a chi-square table, you need to know the degrees of freedom. But unlike the goodness of fit test, where the degrees of freedom is number of categories -1, it's not the case here. Here we have number of rows -1 times the number of columns -1. Okay, that's how you calculate the degrees of freedom. So let's do that for this example and see how it works. Yeah. So here we have how many rows, how many categories, or how many rows in the row. Yeah, row is here 1, 2, 3, and how many columns? 1, 2, 3. So you have 3 rows and 3 columns. So you can use the formula to find the degrees of freedom. Okay. Okay. Again, the degrees of freedom, the formula is exactly, you can understand the formula exactly the way we have understood for hypothesis testing. That is, how many values in the table are free to change, just like we did that example in the seminar. Taking an example of 3 or 4 students and then adding the numbers to 10, just like that, we can see that how maintaining the given row and column totals used in the calculation of the expected values change, and how the degrees of freedom change. Okay, so that is how many values in the table are free to change, like the degrees of freedom. Yeah. So you can use the same with 2 by 2 table and try that out and see how many cells will have the degrees of freedom. Yeah, how it is playing a constraint on the total degrees of freedom. Yeah, so you can do the same and see how degrees of freedom is effective here. Yeah. Okay, so in this case, number of rows is 3, number of columns is 3, and so the degrees of freedom will turn out to be 4 using this formula. Okay, now we can use the degrees of freedom and the chi-square table to find the critical value. So you can see that our chi-square value was 16.68 and it lies somewhere here between these two values. That is between these two values. That is at 0.5% level. Yeah. So the critical value 16.68 is larger than the critical value at 0.5% level, which clearly means that our chi-square statistics is significant at this level, at 0.5% level, indicating that the data shows a significant deviation from independence. So you can reject the null hypothesis. So you can reject the null hypothesis, that is, there is no dependence. And so we can conclude that there appears to be an association or dependency between the hair color and the eye color in men. Okay, so this is how you carry out a chi-square test. Okay, so the first step for carrying out a chi-square test on a contingency table is state the null hypothesis, state the alternative hypothesis, calculate the row, column, and grand totals, calculate the expected frequency, calculate the chi-square statistics for each cell, and then compare it with the chi-square critical value for the given degrees of freedom. Then conclude it by stating whether it is chi-square is not significant or significant to accept or reject the null hypothesis. Okay. Okay, now there is one more thing which we need to understand here. Yeah, if we find that there is an association between the categories, we can identify where the largest deviation from independence occurs by just looking at the calculated values of chi-square for each cell. Okay, that is, if I now take individual chi-square values for each cell, so this is a chi-square value for each cell. Okay, I'm going to represent that. Okay, so each cell gives the individual chi-square value for each cross category, and this is how we calculated the chi-square for each cell, isn't it? And overall chi-square value will be the sum of all of this. Yeah, that's how we got the total chi-square value. If you add them all up, you will get chi-square is equal to 16.68 by adding them all up. Yeah, that's what we have just done. Yeah. Okay. So red hair with blue eyes shows the most significant deviation from the independence, as it has the largest contribution to the overall chi-square value. Look at that, 5.3 is the largest value here, and hence has the largest contribution to this sigma chi-square value, towards the total value of the chi-square statistics. So that means this is the cause of the deviation from the independence. Yeah. Okay. Now, another thing, important thing here is when a contingency table is small, like the 2x2 table, where the degrees of freedom is only 1, we can apply a correction in the calculation of chi-square value. This is only for a small contingency table with 1 degrees of freedom. Okay. So the correction is known as Aids continuity correction and is applied as follows. So instead of having just observed frequency minus expected frequency whole square in the numerator, we have minus 0.5. Okay, so you subtract 0.5. So when you have something in the numerator, When you subtract something in the numerator, what happens? This reduces the magnitude of the difference between the observed and expected frequency of each cell, isn't it? So overall chi-square will go down, fall down, yeah? It will reduce the overall chi-square. So H continuity correction will reduce the overall chi-square value. That means the difference is getting closer and closer. Difference between the observed and expected frequency is getting closer and closer. So it's usually only applied for a small contingency table, okay? Okay, now what I want you to do is try this example, yeah? So you have to, what you have to do is follow the hypothesis step, the steps for the hypothesis test, for chi-square test, and state the null hypothesis, state the alternative hypothesis, then calculate the expected frequency for each cell, okay, for each cross category, okay. For each cell, calculate the expected frequency, write it in a bracket in the same table. Please use your notebook, write each category, then find the chi-square value for each cell, and then find the sum of all the chi-square value, okay? Okay. So, then perform the chi-square test at 5% level. And once you finish that, apply the H continuity correction because it's a small table, yeah, 2 by 2 table, 2 by 2 contingency table. Apply this, that means find for each cell this value and then sum it up to find the total chi-square. And then carry out the test once again and see what you observe from that, okay? Good. So now you know how to perform a chi-square test on a contingency table. Okay, that's all for now in part 2. See you all in seminar.